Welcome to our deep dive into the world of automotive communication protocols. In modern vehicles, electronic control units or ECUs rely on a variety of protocols to communicate, diagnose, and calibrate systems. Today we'll explore the essentials of OBD, UDS, DOIP, and XCP protocols, which are foundational for diagnostics, data acquisition, and vehicle management. Understanding these protocols is crucial for engineers, technicians, and anyone interested in how vehicles operate at a digital level. Let's start by looking at the basics of how data is structured and transmitted in automotive systems, setting the stage for a detailed journey through each protocol. Automotive diagnostics data is often organized in bytes, with each byte or group of bytes representing specific information. One key concept is the parameter ID or PID. PIDs are used to identify the type of data contained in a message, such as engine RPM or mass airflow sensor readings. By referencing a PID, diagnostic tools can request and interpret real-time data from a vehicle's ECU. This system allows for efficient and standardized communication, making it easier to monitor vehicle health and performance across different makes and models. Onboard Diagnostics, or OBDI, defines a set of services that diagnostic tools can use to interact with a vehicle. Each service is identified by a hexadecimal code, such as 0x01 for showing current data or 0x03 for retrieving stored diagnostic trouble codes. These services enable technicians to read live sensor data, view freeze frame data, clear trouble codes, and even control certain onboard systems. The standardized nature of OBDI services ensures compatibility and simplifies the diagnostic process for a wide range of vehicles. Let's look at a practical example using the intake air temperature PID. When a diagnostic tool requests this data, it sends a specific message to the ECU. The ECU responds with a value which is then converted using a formula. For instance, if the response is 50, the physical value is calculated as -40 plus the received value, resulting in 10 degrees C. This conversion process is typical for many PIDs, ensuring that raw data bytes are translated into meaningful, real-world measurements for technicians and engineers. OBDI protocol provides a comprehensive list of services, each designed for a specific diagnostic or control function. These include showing current data, freeze frame data, reading and clearing diagnostic trouble codes, and testing results from various sensors. Each service is accessed using a unique code, allowing diagnostic tools to communicate efficiently with the vehicle's systems. This structured approach streamlines the process of vehicle diagnostics and repair, making it easier to pinpoint and resolve issues. Beyond basic OBDI services, modern vehicles use advanced diagnostic and communication management protocols. These include diagnostic session control, ECU reset, security access, and communication control. Each function is identified by a service ID or SID and may include subfunctions for more granular control. This layered approach allows for secure, flexible, and robust management of vehicle diagnostics, ensuring that only authorized tools and users can access sensitive systems or perform critical operations. Input and output control functions allow diagnostic tools to interact directly with specific vehicle components. For example, input-output control by identifier enables remote activation of routines, such as testing actuators or sensors. Additionally, stored data transmission and routine control services provide mechanisms for uploading, downloading, and managing diagnostic information. These capabilities are essential for in-depth diagnostics, calibration, and system validation during both development and maintenance. Data transmission is a core aspect of automotive diagnostics. Services like read data by identifier, read memory by address, and write data by identifier allow diagnostic tools to access and modify ECU memory. These functions are critical for reading sensor values, updating calibration parameters, and performing advanced diagnostics. The ability to dynamically define data identifiers and periodically read data ensures that engineers can monitor and adjust vehicle systems in real time. Diagnostic protocols messages are structured using service IDs SID, subfunctions SBF, and negative response codes NRC. The SID identifies the main service while the SBF specifies the exact operation within that service. If a request cannot be fulfilled, the ECU responds with a negative response code indicating the type of error. This structured messaging ensures clear communication between diagnostic tools and vehicle systems, making troubleshooting more efficient and systematic. A diagnostic tool sends a request. The ECU can respond in two ways: with a positive response confirming the requested action, or with a negative response, indicating an error or unsupported function. Positive responses typically echo the requested service with additional data, while negative responses include a code explaining the issue. This feedback mechanism is essential for reliable diagnostics, ensuring that technicians can quickly identify and address problems. Modern diagnostic protocols support uploading and downloading data to and from the ECU. Services like request download, request upload, and transfer data enable technicians to update software, calibrate parameters, and retrieve logs. These operations are vital during vehicle development, software updates, and advanced troubleshooting, ensuring that the latest configurations and data are always available for analysis and improvement. Routine control services allow for the execution of predefined routines within the ECU, such as self-tests or calibration sequences. File transfer services, on the other hand, enable the movement of larger data sets such as firmware or configuration files. Together, these capabilities provide a robust framework for maintaining and updating vehicle systems, supporting both routine maintenance and complex engineering tasks. Diagnostics over Internet Protocol, or DOIP, is a modern protocol that leverages standard network technologies for vehicle diagnostics. The DOIP frame includes fields for source and target addresses, protocol type, payload length, and version. This structure enables efficient and scalable communication between diagnostic tools and vehicle ECUs, supporting advanced features like remote diagnostics and over-the-air updates. DOIP supports a variety of payload types, each identified by unique code. These include vehicle identification requests, routing activation, alive checks, and diagnostic messages. The protocol reserves specific ranges for future expansion, ensuring flexibility as automotive technology evolves. By standardizing payload types, DOIP simplifies the integration of new diagnostic tools and services across different vehicle platforms. Within the AUTOSAR framework, DOIP is implemented using TCP/IP as the transport layer and UDP/IP as the network layer. This approach leverages widely used networking standards, enabling seamless integration with existing IT infrastructure. As a result, automotive diagnostics can benefit from the reliability, scalability, and security features of modern network technologies, paving the way for advanced connected vehicle services. Adoption of DOIP brings several advantages to automotive diagnostics. By using standard network protocols, DOIP enables faster data transfer, remote access, and improved scalability. It also supports advanced features like over-the-air updates and cloud-based diagnostics, making it a key enabler for the next generation of connected vehicles. These benefits help manufacturers and service providers deliver better, more efficient support to vehicle owners. XCP protocol, or Universal Measurement and Calibration Protocol, is widely used in the automotive industry for measuring and calibrating ECUs. Engineers rely on XCP to read live measurement data and write parameters during development, testing, and in-vehicle calibration. XCP supports multiple transport layers including CAN, Ethernet, and FlexRay, offering flexibility for various applications and environments. XCP communication involves several packet types, each serving a specific function. Command transfer objects CTO send commands, while data transfer objects DTO carry measurement or stimulation data. Other packet types include command response, error, event, service request, data acquisition, and stimulation packets. This structured approach ensures efficient and reliable communication between the XCP master and slave devices, supporting complex measurement and calibration tasks. 812 files play a crucial role in XCP-based systems. They describe ECU data objects, such as parameters, maps, and variables, along with their addresses, types, and conversion rules. 812 files also define communication parameters between the XCP master and slave, ensuring that data is interpreted correctly. This standardized approach simplifies the setup and operation of measurement and calibration systems, making it easier for engineers to work with complex ECU. XCP frame consists of a header, payload, and tail, each serving a specific purpose. The header identifies the packet type such as command, response, or event. The payload contains the actual measurement or stimulation data, while the tail ensures alignment and consistent frame length. This structure supports reliable data acquisition and calibration, providing precise timing and identification for each data packet. Summary: automotive communication protocols like OBD, UDS, DOIP, and XCP form the backbone of modern vehicle diagnostics, calibration, and management. As vehicles become more connected and software-driven, these protocols will continue to evolve, supporting new features like remote diagnostics, over-the-air updates, and advanced data analytics. Staying informed about these technologies is essential for anyone working in the automotive industry, ensuring that vehicles remain safe, efficient, and reliable for years to come.